So let's go to an example actually, or an application of a matrix multiplication. And so I have here a finance application which is related to credit ratings. So you might know that there are these different agencies which are called credit raters. So Moody's and Standard and Poor's are very well known, and Fitch is another one which is fairly big. And what they do is they issue credit ratings to usually to different financial instruments, or for instance to bonds that are issued by firms, but also to bonds that are issued by countries, by sovereigns, in which these firms or these countries borrow money basically from investors. And what these ratings do is basically they say, so how credit worthy is this issuer of this bond? So is it a very reliable firm or a very reliable country in terms of paying back and paying the interest on the bond, or not so much? So on the top here, you see, so in these columns, basically for each of these different agencies, you see these different ratings that they issue. So you're probably all familiar with the notion of AAA, which means very high investment grade, so very high reliability of getting back your money if you lend money to these firms. And it goes all the way down to what's called D, and D just means in default, so basically sort of near bankruptcy or in bankruptcy. So there's a whole list here, so there's a lot of different categories where and they have different names, as you can see there. And the top half, more or less, called investment grade. So those are the ones that say pension funds might be allowed to invest in, whereas the bottom more or less half are called junk bonds. So they are the sort of less reliable issuers in the view, at least, of these credit raters. So the further the letters down the alphabet, basically, the worse the credit status of these issuers. So as I mentioned, this is applied not only to firms but also to countries. So here you see a slightly dated, I guess, a picture of credit ratings of countries. So as you know, of course, countries also sort of regularly issue bonds to fund their budget essentially. And many at least a number of countries have AAA status, and many have AA status. So all of this is pretty good. But it goes all the way down to sort of less creditworthy countries, at least in the aftermath of the financial crisis in Europe. Of course, Greece was sort of, well, sort of a less viewed as a less creditworthy issuer, and indeed bonds issued by Greece had been written down by quite a bit during the financial crisis. So this is just for just having a view of what these credit ratings basically do. So what are we going to do with this? But as I just said, the meaning of this rating means, how creditworthy is this firm or country? So basically, that means, what's the probability that this country, in our case, would default on paying its interest on the bond, or paying back the principal of this bond. And now, typically, if you have a high credit rating, of course, it's very unlikely that you will immediately, from one year to the next, default. What's more likely, actually, is that when you have higher credit rating today, is that next year, if things go a bit poorer, or if you happen to be in a corona crisis, for instance, perhaps your bonds go down one notch in this schedule, so they might not default immediately, but the ratings might change. So ratings might go down, and on the other hand, ratings might also go up. And of course, wherever you are in this schedule, so if you're AAA, there's a large probability that you might remain in the AAA category, but you might go down one notch to AA, for instance. Whereas if you're already close to the default, then well, you might go up. So if you have a C rating, which is a junk bond rating, you might go up to a B rating, but you might also go down to a default rating, or you might stay, of course, in your category. So I want to give a very simplified example here where we would have just three ratings. I'll call them A, B, and D. So A will be the best rating, B would be the slightly worse rating, and D will be default. So what that means is that if you're an A-rated firm, well, if you continue to do well and presumably, since you are given this A rating, this happens with a high probability, then you will stay next year in the in this A-rated class. So let's just assume for the example's sake that there's a high probability, 80%, of remaining in your A category when the credit rater has given you an A rating this year. But of course, you might go down, as I just mentioned. So if things go a bit poorer than you expected as a firm or as a country, then the next year you might move down one category to the B rating in this case, which is the slightly worse rating. And of course, if things go very poor, but that happens with a low likelihood, then you might actually default right next year. So that's only a small probability. I will just take that to be 5%. So you might move at once 2 steps in our model here from A rating to default to D, but only with a very small probability, in this case of 5%. So similarly for B-rated firms, with a large probability they will stay in the B rating, but if things go better than before, they might move up to the A rating, or they might move down towards into default. And we're also going to assume that once you're in default, you remain in default, so you're irrevocably lost, basically. So what we can do is we can collect this information, these transitions, if you wish, from one rating class to the next, in terms of a transition matrix. How should we read this matrix? Bold capital T. Well, if you look at the different columns, they will sort of denote the probabilities of going to any other class of rating. So the first column in particular will be what is your transition probability if you start out in the A rating class? What is your transition probability of remaining in the A rating? That's the 80%, the 0.8 that you see on top there. And as I mentioned in my example, there's a 15% chance, 15% probability, or 0.15 probability of moving down to the B rating, and there's a 5% or 0.05 probability that starting out from the A rating class, you might move to the default probability. So that's the first column. Similarly, second column will encode these transition probabilities for the B rating. So again, 80% chance that you remain in B, but there's 10% likelihood of going up, 0.1, and there's also a 10% likelihood of going down, 0.1. So these are just the assumptions of this particular model. And finally, the final column, of course, will be once you're in the D category, so default category, there is 0% chance of getting out of there. So 0 probability of going to the A rating, 0 probability of going to the B rating, and hence a probability of 1 of remaining in class D. So this just summarizes basically the information that we have from these probabilities of changes in rating from one year to the next, depending on what class you start out in. So T21, as I wrote down there, T21, well, what element is that? That will be the second row, the first element over here, the first column over here, 0.15. That is the probability that a firm that starts out in rating A, which is this column, basically migrates to rating B, which is basically this row, after 1 year. So that's 15%. That's how we should read this matrix T, this transition matrix T. Okay, so that's just a definition, that or notation that that's going to turn out to be convenient. So let's work with that. So let's ask a question. So suppose that I start with a collection of firms, and half of those firms start out with an initial rating of A, so the highest rating, and half of those firms start out with rating B, and of course, by assumption, just none are yet in default. And then question that might be interesting is how would those collection of firms, how would they be distributed across these rating classes next year? And of course, we will have to use these transition likelihoods, these transition probabilities that are sort of written in these matrices. So let's have a look how we might be able to write this. the answer turns out to be, well, let's take this particular column vector. So this is column vector. It says how many, what proportion of firms are in my A category. Well, it was 50%. What proportion of my firms start out in my B category? 50%. And what proportion of firms start out in my D, my default category? Well, it was 0. Now, how do we then compute the distribution of these firms over these 3 different categories next year? Well, that is exactly by applying this transition matrix, which is again here. So this is this matrix T. By multiplying that matrix essentially with this column vector of these different weights, these different proportions of firms. So let's see whether we can see that that is true. So, for instance, we would like to know how many firms would like to be in category A next year. So which firms would that be? Well, it would either be those firms that today, this year, are already in category A and stay there. So that's 80%, 0.8 times half, 0.5 that are already in A this year. So that contributes 40%, 0.4 if you do the computation. But it also includes those that are in category B today, which is the other half essentially, but move up, which comes with a likelihood of 10%, so that was this 0.1. So indeed, what we get as the first number here is 0.8 times 0.5, which is 0.4 or 40%, plus 0.1 times 0.5, those which start out in B but which go up to A, is 0.05. And if I add those two up, these 40% from A and the 5% from B, I indeed get this 0.45%. And you can see that what we're doing here essentially is exactly matrix multiplication. Taking the first number here in this first row times the first number in this column, the second number in the first row times the second number in the first column, or in the column, plus the third number, which is 0 actually, times the third number over here, which is actually also 0. So that adds up indeed to 0.45. And same thing, if you are, second example, are interested in how many firms will have defaulted by that time, after this year. Well, that will include those that have defaulted directly from A. Well, that was just a mere 5% of those who started out in A. So I have to multiply that by the number of firms, or the proportion of firms that start out in A. So 0.05 times 0.5, that's 2.5% if you work it out, plus those that start out in B, and 10% of those actually go into default, so that's plus 0.1 times 0.5. Together that adds up to 0.075 or 7.5%, so that's the second thing. And same way, you can verify that this will be then the remaining fraction who will be in B by taking this row and multiplying it again by that column. So indeed, matrix multiplication here, using this transition matrix, has the effect of computing exactly what you want, in the sense that it computes what will, given the distribution of firms today, what will be the new distribution of firms next year. So well, that's a first step. So that's nice to see. So we can use this matrix multiplication to see indeed what the result is of those transitions from rating class, from one rating class to the other, over the course of a year. So that's just multiplying the transition matrix by the initial distribution of firms over the different rating classes, like this. Now we can go on actually. So we might also ask, well, today we are still, again, I start out with this distribution half in class A, half in class B. I just answered, what's going to happen next year, but I might also be interested, of course, what's going to happen after 2 years. So what's the likelihood, or what's the distribution of all these firms if I just let them go on for 2 years, given this particular transition matrix? So now what would you have to do for that? Well, one way of seeing this is, well, this first bit is what we computed just on the previous slide, essentially, right? So the answer to multiplying this transition matrix with the initial input here was the distribution of firms after 1 year. To get what happens after the second year, I just once again multiply this with the same transition matrix. So I start out with the answer that we had after year 1, and by applying or multiplying again once more with this same matrix T, the same transition matrix T, I will find, I will again have to first computed the red bit. Now I do the new computation by again multiplying that, the resulting column vector, multiplying that again by this transition matrix, and I get a new vector of distributions, a column vector of distributions of firms that turns out to be this. So you can verify that if you wish. So what we learned from that is indeed, we can read off from this vector, indeed 14.5% of the firms will have defaulted after 2 years. Now, one thing to notice is that we could also have done this computation in a different way. We could also have said, well, so what I just did, I just first computed the red bits, right? I did this computation here. I multiplied the red matrix with a red input vector. So just basically multiplication that we did on the previous slide. Gave me a result, and I multiplied that again with this transition matrix, and that gave me the end result after 2 years. What I could have done as well is I first multiply these two transition matrices. I have here two matrices, 3 by 3 matrix T, and I can multiply that using matrix multiplication with itself, and that's what I've written down here. So these first two matrices are again written down here. I can do the matrix multiplication, and I invite you to check some of these numbers. If I do that, so for the first one I would have 0.8 times 0.8 plus 0.1 times 0.15 plus 0 times 0.05. Apparently that gives me 0.65 and a half. Now the nice thing is that we can interpret this object here, this result of multiplying the first transition matrix with the second transition matrix, well, they are the same in this case, as a 2-year transition probability. So what this says is, well, if you start out today in category A, what's then the likelihood that you end up in category A? Well, apparently that's exactly the 65.5%. That's my transition probability of, if I start out today in A, after 2 years, I will again be in A. How does that arise? Well, through two ways. Either I stay in A the first year and then I stay in A the second year as well. That's the 0.8 times the 0.8. Or I move down to B in the first year. That happens with my 0.15. But that next year I move up again, which happens with 0.1, back to A. So then I will also end up again in A. So this number indeed exactly captures all the firms, all the ways a firm might end up in A after starting in A. And the same actually goes for all these other numbers here. So again, we can read off basically from this 2-year transition matrix, which is just the product of the 1-year transition matrix with itself, the transition probabilities for each of the classes for a 2-year period. So for instance, if I'm interested in the question, well, if I start out in B, what's the probability that after 2 years I will be in default? You can read off, I start out in B, that's this column. Ending up in default will be the last number, and it's going to be 18.5%. Similarly, if I'm interested in 10-year transition probability, I might do the same thing, but then 10 times. So I keep on multiplying with the same matrix T, but now 10 times. So here indeed is this example that I just said was a probability to stay in A after 2 years. Well, it is 0.8 times 0.8, staying in A twice essentially, plus the probability of moving down and moving up, back up again. That's moving down is the 0.15, moving back up is the 0.1, plus probability of going to D at first and then going back, but this going back doesn't happen at all. It has a 0 probability, so that contributes 0. So this is exactly what we're after. Let me note at the end some final things we relate to matrix multiplication. So what I did here was I multiplied these two matrices, and here I multiplied these two matrices, and I multiplied that by a vector. And basically what I used here was it shouldn't matter what I'm doing, whether I'm first multiplying this matrix with this vector and then multiplying the result with this previous matrix, should be the same as if I first multiply these two matrices with each other, giving me this, and then multiplying that end result with my initial vector. That's basically what this thing says. It shouldn't matter if I have matrix A, matrix B, and a matrix C, which of these multiplications I carry out first. So whether I first do what's in the brackets here, whether I first compute B times C and then multiply that resulting matrix with matrix A, or on the other hand, whether I first multiply A times B and then multiply that on the left hand side with C, that will give the same result. So that's one property. Another property, which is called the distributive property, which is also shared actually with normal numbers, right? So this is actually also the same if you do regular multiplication with regular numbers. I do 10 times 3 times 5. It doesn't matter whether I first compute 3 times 5 and then multiply by 10, or whether I first do 10 times 3 and then multiply that by 5. Same way here, we have the distributive property, so it doesn't matter whether I first add up B plus C and then multiply that result by A, or whether I compute separately A times B and A times C and then add those up. So that's, again, something that's familiar from normal numbers. So the final one we actually already encountered. We cannot, like normal numbers, just assume that we can interchange the order of multiplication. So A times B, if A and B are matrices, are not necessarily equal to B times A. And we have seen an example of that actually a bit before in the previous video. So that also means that these pretty well-known quadratic identities that we covered in the first lecture, they don't hold exactly the same way as they do for real numbers here for matrices. So in particular, if we look at a plus b squared, then that's not going to be the same as a squared plus 2ab plus b squared in general when these a's and b's are matrices. And the reason is a times b is not b times a, so I cannot add those up. A final thing that I'd like to mention here is the thing which is called the identity matrix. So the identity matrix in this case is a square matrix. So if it's an n-dimensional identity matrix, it would be an n by n matrix. It could be 2 by 2 or 10 by 10, what you wish, but it should not be rectangular, it should be square. And identity means that there will be ones on the diagonal, so this is obviously the diagonal, and zeros off the diagonal. So we call that the identity. So why is that the identity? Well, if you multiply any matrix with this identity matrix, with this I, then it remains the same, whether I multiply it on the left hand side or on the right hand side. So here's an example. So here's this identity matrix in 2 dimensions, so it's 2 by 2 square matrix. If I multiply it by any other regular 2 by 2 matrix, what do we get? Well, in the top left hand corner, you get 1 times A plus 0 times C, so that's A. Top right corner, you get 1 times B plus 0 times D, so that's B. And then bottom left, we get 0 times A plus 1 times C, that's C. And indeed, bottom right, 0 times B plus 1 times D is D. So indeed, we get back the exact A, B, C, D matrix that we started out with. So multiplying by an identity matrix basically does nothing, just like multiplying by 1 for regular numbers. There's nothing to the number. And we can also apply this to a vector rather than a matrix. So here I can have a 2 by 2 matrix. I can multiply this with a 2-dimensional column vector. So what happens is, well, 1, 0 times x, y gives me 1 times x plus 0, y. That's x. And the bottom element will be 0 times x plus 1 times y. That's y. So again, multiplying any 2-dimensional vector with this 2-dimensional identity keeps this vector exactly at what it was. So that's the effect of an identity matrix, and we're going to need that a little bit later on. So next bit will be the inverse of matrix. So let's get there in the next video.